The language of data science. Python has become the backbone of modern data science, thanks to its simplicity, readability, and vast ecosystem of powerful libraries. Whether you're cleaning data, training deep learning models, or visualizing trends, Python offers the flexibility and tools needed to bring data to life. As we move forward, we will explore the essential libraries that every data scientist should master: NumPy, Pandas, Keras, and OpenCV. Understanding NumPy. NumPy, short for Numerical Python, is the foundational package for scientific computing in Python. It introduces the concept of arrays, which are faster and more efficient than traditional Python lists. With NumPy, you can perform mathematical operations such as array addition, subtraction, and multiplication with ease. The np.array function lets you create arrays, while np.zeros and np.ones help initialize them. To generate sequences, np.arrange and np.linspace are invaluable. Statistical operations become seamless with np.mean, np.std, and np.var. For matrix operations, you'll use np.dot for dot products and np.linealgel.inv for finding the inverse of a matrix. Finally, reshaping and flattening arrays is a breeze with np.reshape and np.ravel. Mastering these core functions equips you with the computational tools to handle large datasets efficiently. Powering data manipulation with Pandas. Pandas takes raw data and turns it into structured, analyzable insights. At the heart of Pandas lie two key structures: series and data frames. A series is a one-dimensional array-like object, while a data frame is a two-dimensional labeled data structure with columns of potentially different types. You'll frequently use pd.read_csv to load data, and df.head and df.tail to preview it. When exploring, df.info and df.describe give you insights into the structure and statistics. To filter data, df.lock and df.illoc are essential. Modifying your data becomes natural with df.drop for removing columns or rows and df.fillNA to handle missing values. Grouping data is done with df.groupby, and merging multiple data frames can be achieved with pd.merge. Sorting with df.sort_values and reshaping with df.pivot or df.melt rounds out a powerful toolkit for any data wrangler. Pandas empowers you to turn chaos into clarity. Deep learning with Keras. Keras simplifies the creation and training of deep learning models. As a high-level API built on top of TensorFlow, Keras allows rapid prototyping of neural networks. The core building block is the sequential model, where layers are stacked linearly. You start by importing keras.models.sequential and defining your model with layers like dense for fully connected layers and dropout for regularization. Activation functions such as ReLU, sigmoid, and softmax control how neurons fire. The compile method prepares the model for training by specifying the optimizer, loss function, and metrics. You then fit the model to data using model.fit, which trains it over several epochs. To evaluate how well your model performs, use model.evaluate and make predictions with model.predict. Saving and loading models is straightforward with model.save and keras.models.load_model. For more complex architectures, the functional API gives you flexibility to build nonlinear layer connections. With Keras, deep learning becomes approachable and scalable. Seeing the data with OpenCV. OpenCV, or Open Source Computer Vision Library, brings powerful tools to work with images and video data. Whether you're analyzing medical scans or building a facial recognition system, OpenCV equips you with the capabilities you need. It starts with reading images using cv2.imread and displaying them with cv2.imshow. You can manipulate image size with cv2.resize and convert between color spaces using cv2.cvtcolor. To draw on images, use functions like cv2.line, cv2.rectangle, and cv2.circle. For detecting features, OpenCV offers algorithms like edge detection through cv2.canny and contour finding with cv2.findContours. You can read video streams with cv2.video capture and process frames in real time. Blurring images is simple with cv2.Gaussian blur, and thresholding is done via cv2.threshold. With OpenCV, computer vision becomes accessible and powerful for every data scientist. Telling stories with data visualization. Numbers can be powerful, but without context and clarity, they can easily overwhelm. Data visualization bridges the gap between raw data and human understanding. With Python, libraries like Matplotlib and Seaborn provide elegant, customizable ways to bring data to life. Using matplotlib.pyplot, you can create line plots with plt.plot and bar charts using plt.bar. For scatter plots, which show relationships between variables, plt.scatter is your go-to function. Histograms to show distribution can be made with plt.hist and pie charts with plt.pie. You can add titles and labels using plt.title, plt.slabel, and plt.elabel, and save your visualizations with plt.savefig. Seaborn builds on top of Matplotlib and makes complex plots more beautiful and easier to create. A simple call to sns.lineplot, sns.boxplots, or sns.heatmap can uncover hidden patterns in your data. Seaborn also integrates tightly with Pandas dataframes, letting you create plots with minimal code. Visualizations are more than decoration. They are tools to communicate results, highlight anomalies, and persuade decision-makers. By mastering them, you elevate your analysis from technical output to compelling narrative. Predicting the future with scikit-learn. Machine learning is a core part of data science, and scikit-learn makes it accessible, reliable, and powerful. Built on top of NumPy and SciPy, scikit-learn provides a consistent interface for training, testing, and evaluating a wide variety of machine learning models. To begin, you load your data and split it into training and testing sets using train_test_split from sklearn.model_selection. You then choose a model, such as linear regression, logistic regression, or random forest classifier. Each model follows a familiar pattern. Initialize it, fit it with model.fit, and make predictions with model.predict. Performance is measured using metrics like accuracy, precision, recall, F1 score, and mean squared error, which can be found in sklearn.metrics. For pre-processing, scikit-learn provides tools like standard scaler to normalize data and one-hot encoder to handle categorical variables. Pipelines help you chain pre-processing and modeling steps into a repeatable workflow using pipeline objects. Cross-validation with cross_val_score gives you a robust sense of model performance. Whether you're building a spam filter, recommending movies, or predicting stock prices, scikit-learn gives you the tools to turn data into prediction. With just a few lines of code, you can train powerful models and gain insights from your data that were previously invisible. The language of patterns, statistics in data science. At the heart of data science lies statistics, the art of understanding patterns in uncertainty. Before you build models or visualize trends, you must first explore, describe, and summarize your data using statistical tools. In Python, libraries like NumPy, SciPy, and Pandas give you access to these methods with simple, readable code. Descriptive statistics are your first lens into a dataset. With np.mean, np.median, and np.mode from SciPy, you summarize central tendencies. To understand variability, you rely on np.std for standard deviation and np.var for variance. Pandas allows you to compute these across entire columns of a data frame using methods like df.mean, df.std, and df.describe. The mean is the most common measure of central tendency and represents the arithmetic average of a dataset. You compute it by summing all the data points and dividing by the number of points. For instance, the mean of the dataset 2, 4, 6, 8, 10 is calculated as 2 plus 4 plus 6 plus 8 plus 10. 5, which equals 6. The mean is sensitive to outliers, which means that extreme values can skew the result, making it less representative of the data. The median is the middle value when the data is arranged in ascending order. If the dataset has an odd number of observations, the median is simply the middle value. If it has an even number, it's the average of the two middle values. For example, in the dataset 1, 3, 5, 7, 9, the median is 5. However, in the dataset 1, 3, 5, 7, the median would be 3 plus 5, 2, which equals 4. The median is a better measure of central tendency when the data contains outliers, as it is not influenced by extreme values. The mode is the value that appears most frequently in the dataset. Unlike the mean and median, a dataset can have more than one mode, or even no mode at all if no value repeats. For example, in the dataset 1, 2, 2, 3, 4, the mode is 2, because it occurs twice. If the dataset were 1, 2, 3, 4, there would be no mode, as each value occurs only once. The mode is particularly useful for categorical data where we want to know the most common category. To understand deviation and variance, we first need to recognize that data points often deviate from the mean. Deviation measures how far a data point is from the mean. In a dataset, each value's deviation is the difference between the value and the mean. For example, for the dataset 2, 4, 6, 8, 10, and a mean of 6, the deviations would be -4, -2, 0, 2, 4. The variance quantifies the extent to which data points differ from the mean. It's calculated by taking the average of the squared deviations. In other words, variance tells you the spread or dispersion of the data. If the variance is large, it indicates that the data points are spread out widely from the mean, and if it's small, the data points are close to the mean. In the dataset 2, 4, 6, 8, 10, the variance would be the average of the squared deviations, 16, 4, 0, 4, 16, which results in a variance of 8. Standard deviation is simply the square root of the variance and provides a measure of spread in the same units as the original data. A high standard deviation means that data points are spread out over a wider range, while a low standard deviation means they are clustered closely around the mean. In the case of our example dataset, 2, 4, 6, 8, 10, the standard deviation would be the square root of 8, approximately 2.83. Standard deviation is often preferred over variance because it's in the same units as the original data, making it more interpretable. But statistics go far beyond summarizing. You can measure relationships with SciPy.Stats.Pearsoner for correlation, helping you determine whether two variables move together. To compare groups, use hypothesis testing. The t-test, implemented as SciPy.Stats.Tist_ind, checks whether the means of two independent samples differ significantly. If you're analyzing proportions or categories, the chi-squared test through SciPy.Stats.Chi2_contingency provides insights into categorical associations. Linear regression, available through SciPy.Stats.LinRegress, helps quantify the relationship between a dependent and independent variable. Probability distributions let you model real-world events. SciPy offers a wide range of them: normal, binomial, Poisson, and more. You can sample from a normal distribution with SciPy.Stats.Norm.RVS, or compute the probability density function using SciPy.Stats.Norm.pdf. Confidence intervals, effect sizes, and p-values all guide how you interpret your results, reminding you that data science is as much about uncertainty as it is about prediction. Understanding statistics is more than just running functions. It's about asking the right questions, understanding what the data can and cannot tell you, and drawing conclusions grounded in evidence. With a strong foundation in statistics, every other tool in the data science toolkit becomes more powerful and more meaningful. In addition to mean, median, mode, deviation, and variance, data science often requires deeper statistical analysis to uncover hidden patterns and insights in data. The concepts of skewness, kurtosis, and normal distribution are critical for understanding the underlying shape of your data, while probability distributions play a fundamental role in modeling uncertainties. Let's dive deeper into these statistical measures. Skewness and kurtosis. Skewness measures the asymmetry of the data distribution. If the data is positively skewed, or right-skewed, the right tail of the distribution is longer than the left, and most of the data points are concentrated on the left side. Conversely, if the data is negatively skewed, or left-skewed, the left tail is longer, and most of the data points are on the right. A skewness value of 0 indicates a perfectly symmetrical distribution. In Python, you can compute skewness using SciPy.Stats.Skew, which will return a positive value for right-skewed data, a negative value for left-skewed data, and close to 0 for symmetric data. Kurtosis, on the other hand, measures the tailedness or peak of the data distribution. A normal distribution has a kurtosis value of 3, but excess kurtosis, which subtracts 3 from the value, is often used in practice. A positive kurtosis indicates that the distribution has heavy tails or outliers, while a negative kurtosis indicates lighter tails. You can compute kurtosis in Python using SciPy.Stats.Kurtosis. A value significantly greater than 0 suggests that your data has extreme outliers, while a value near 0 means the distribution is relatively light-tailed. Normal distribution. The normal distribution, also known as the Gaussian distribution, is one of the most important probability distributions in statistics. It is symmetrical and follows the bell curve shape. Many statistical tests and machine learning models assume that the data follows a normal distribution, as it simplifies many calculations and allows the application of parametric tests. In Python, you can visualize the normal distribution using Matplotlib and Seaborn by plotting the data over a curve generated by scipy.stats.norm.pdf. For example, generating a random sample with np.random.normal and plotting it can show how the data is distributed along the bell curve. A critical feature of the normal distribution is the empirical rule, also known as the 68-95-99.7 rule. This rule states that for a normal distribution, 68% of the data falls within one standard deviation of the mean. 95% of the data falls within 2 standard deviations. 99.7% of the data falls within 3 standard deviations. This rule is useful for understanding how data behaves and can help in detecting outliers. Hypothesis testing. Hypothesis testing is a fundamental tool in statistics used to make inferences about populations based on sample data. The process begins with forming a null hypothesis, H0, which states that there is no effect or difference, and an alternative hypothesis, H1, which states that there is a significant effect or difference. The goal is to evaluate the strength of the evidence against the null hypothesis. In Python, scipy.stats provides functions to perform common tests. The t-test, scipy.stats.tist_nd, is used to compare the means of two independent samples, determining if they are significantly different from one another. For comparing proportions or categorical data, the chi-squared test, scipy.stats.chi2_contingency, is used to examine whether the frequencies of categories differ from the expected frequencies. The p-value is a crucial element in hypothesis testing. It quantifies the probability of obtaining a test statistic as extreme as the one observed, assuming the null hypothesis is true. A smaller p-value, typically less than 0.05, suggests strong evidence against the null hypothesis, indicating that the observed data is unlikely under the assumption of no effect. Confidence intervals. A confidence interval provides a range of values within which the true population parameter, such as the population mean, is likely to lie, given the sample data. A confidence level, such as 95%, indicates that if you were to repeat the sampling process many times, 95% of the confidence intervals you compute would contain the true population parameter. In Python, you can compute confidence intervals using scipy.stats.t.interval for the mean, which requires the sample size, sample mean, standard error, and confidence level. This is important for determining the precision of your estimates and understanding the potential error margin. Correlation and causation. While correlation measures the strength and direction of a linear relationship between two variables, causation indicates that one variable directly influences the other. It is crucial to distinguish between the two in data analysis. Just because two variables are correlated doesn't mean one causes the other. In Python, you can measure correlation using scipy.stats.pearsoner for Pearson's correlation coefficient, which ranges from -1, perfect negative correlation, to 1, perfect positive correlation. A correlation of 0 indicates no linear relationship. However, correlation does not imply causation, and advanced techniques like regression analysis or causal inference are required to establish causality.